All right, so this is example 2.2, and we want to determine the internal loadings at point C. The shaft is supported by a truss bearing at A and a journal bearing at B. So we want to figure out what's the internal loading at point C. So for this, we need a section. When we section, we can either use the left-hand side or the right-hand side of the shaft. Here, I want to go with the left-hand side. Notice regardless of which side I pick, I have a support reaction. So at this one, I have a support at A. Over here, I would have a B. So I would need to solve for those first and then actually take the section. So what I've done over here is already started a little bit the free body diagram of the shaft. I know I have a 900 Newton force pointing down over here at D. At B, I have a bearing. Remember, the bearing at B is a journal bearing. So these bearings are not going to limit any thrust in this direction, only in the vertical direction. Since I have 900 pound force going down here on the right side, and I have a distributed load going down on the left-hand side of this bearing, I'm going to assume that this guy is going to keep this shaft in equilibrium by moving up. So next I have these distributed load, but I don't want to use that. Instead of my free body diagram, I want to replace it with just a point load. So the way we do that is we get the area, right? So this one is 600 newtons per meter because there's 2 meters. 600 times 2 is 1,200 newtons, and it would go right at the center of this area. This being a rectangle, pretty easy to see that the center is right at point C, which is 1 meter, right, each way from the start of the distributed loading. Now let's go ahead and figure out what the reactions are at A. This is a journal bearing, so it has a capacity to have an X component. I'll call this AX, and a Y component. So I'm just going to assume positive in the Y. Again, and so before we actually solve for the internal reactions, right, we need to solve for the support reactions. So let's go ahead and do some statics here. I'm going to go ahead and sum the moments at this point A so we can solve for B. So summing the moments at point A, making them equal to 0. Remember our convention, counterclockwise, it's positive, right? None of these are going to cause a moment. The 1200 Newton force will, so 1200. It's a distance of from point A to the centroid of 2 meters. Okay, and if we're pinned here, this force is going to cause a clockwise or a negative moment. Next, we have the reaction at B, which is what we're trying to solve. So if I'm pinned at A and I push up over here at B, it would make the whole thing rotate counterclockwise. So that's a positive moment. The force is this B, and the distance is going to be our distance from A to point B. So we got 1, 2, 3, 4.5 meters. And then finally, we have the 900 Newton load. It's pointing down, so it's going to make it rotate clockwise. So it's a negative moment. So it's 900 times the distance. Well, the distance from A to B is 4.5. If we add another 1.5 to that, there's going to be 6 meters. The sum of those moments must be equal to 0. So here we would solve for B. How I would solve for B? Well, since B is positive over here, I would move this to the other side, this to the other side, and then divide by 4.5. So 1,200 times 2. Remember, now it's positive because I'm going to move it to the other side. Plus 900 times 6. And then that answer divided by 4.5. This gives me a force of 1733, 1,733.3 newtons. So we have the force at at B. So with this, if you're trying to save time, you might be tempted to go ahead and use the right-handed section. I already have my unknown and move on. I like to always finish the statics to make sure this number that I got is correct. How am I going to do that? Well, I'm going to do so by summing moments now at point B, figuring out what the Y component is, and then summing the forces in the Y direction to make sure all of that equals to 0. Again, why I do that? Because I want to really make sure that my reaction forces are okay before I continue doing any extra work. So now summing moments at point B, making those equal to 0. Remember, anything that is counterclockwise, it's positive. I'm now at B. Summing moments, I'm going to start here from left to right. So first I'll start with our reaction force AY. Notice AX, it crosses, right? Its line of action is through point B, so it's not going to generate a moment. Only AY, right? We said the distance between A and B was 4.5. Let's check again. 1, 2, 3, 4.5, 4.5. And if I'm paint at point B and I push up, it'll make it rotate clockwise, so that would be a negative moment. Next, I have the 1,200. It's in the opposite sense, right? So it's going to be a positive moment, 1,200 times the distance to B. So from point C to B, it is 2.5 over here. Next, the force B passes at point B, right? This is not going to contribute right here, but we have the 900 Newton force. So 900 is the force. The distance is 1.5 from B. And if I'm pinned here and if I push down, that's going to cause clockwise or a negative moment. So that's our equation. I can solve for AY over here. Well, what I would do is actually, because it's negative, I would actually move it to the other side, keep all of this, and then divide by a positive 4.5. So that would mean I have 1,200 times 2.5 minus 900 times 1.5. The answer divided by a 4.5 positive. Then I get 366.6 newtons. So now I know my B force, or if we want to be super specific, our BY. And we know our AY. Then I would check if I sum the forces in the Y direction, does it equal 0? So AY, we got a positive number, which means the direction that we assume was correct. So we assume up, so we would have plus 366.6. Next, minus 1,200, because it points down. BY points up, we got a positive number, means that direction was correct. So we're going to add 1,733.3. And then the last one is the 900. It's pointing down, so that's negative in the Y. So minus 900, and I asked the question, does that equal 0? But now I'm getting a value very close to 0, 0.1. So there we go. So now I got some confidence, so I can move on to the next step when I take these values. Now I said I was going to use here the left-handed section, or this one over here. So let's draw the free body diagram. It looks something like this, just a teeny bitty little shaft over here. We got at point A, let's draw point A. We have a force. A, we said, was 366.6. So I'm going to color it blue because I know it's a known now. I'm pretty confident that that's the force, reaction force from that bearing. So there's that guy. And then I have some distributed loading, right? So somewhere here, I have some distributed loading, like so. This is point C. Now this magnitude of this distributed loading is 600 newtons per meter. And I need some distances, right? So this distance from here to there is 1 meter. And if I'm just going to C, that's also another meter. So 1 meter there. Now before I can actually put here or solve for the reaction forces, right at this section, right, I wouldn't have a normal. So I would put it in the positive convention, which is stretching out. So that's the normal. Next, I need a shear. And remember, a positive shear is one that would spin this element clockwise. So positive in this case is actually pointing down. That's the shear. And the moment, I'm looking for like a happy face. So the moment would be something like this. So that's the direction of my moment. It would be on this right hand cut. It would be counterclockwise. But I have the distributed loading. So I guess I could use this one. Or rather, what I would do is just go ahead and simplify this distributed load into a point load. how to do that. Again, here's free body diagram number 3. Here's our point A. The reaction force from the bearing, 366.6 newtons. And then I'm going to convert this distributed load into a point load. The magnitude is 600, remember? And I'm just looking at the 1/2, so that's 1 meter. So 600 times 1 is 600. Where do I put it or place it is going to be right in the middle, because this is a rectangular square area, right? So I'm going to put it right here. There's a 600 Newton force. And next, let's put some distances. Oops, I bumped the camera, sorry. Hold on, let me stabilize you. There you go, that way you don't get dizzy. So this over here is gonna be 1/2 meter. Sorry. That distance here is 0.5 meters. And then the distance to point C is going to be, this distance here is another 1.5 meters. So total of 2 meters. That's our point C. And let's put our internal loads. Positive normal, stretching again. Shear points down, that's a positive shear because it makes it spin clockwise. And our reaction moment here counterclockwise. So here we go. Now we're working with this free body diagram. And to solve this one, it's just a matter of doing equations, right? Equilibrium equations. We would do sum of forces in the x equal to 0. What do we have? And maybe right now your brain is going, Why? Because at A we had a thrust bearing, right? The thrust bearing is capable of resisting any motion, any translation of the shaft. So it's capable of producing a reaction force here on the x direction. I didn't do the equation of equilibrium for this free body diagram, but by inspection we can see all the other forces are up and down, which means our AX has to be 0. And that's why I didn't write it over here. So mentally I did it, but I need to remind you there's no reaction force here in the x. That's very important because it means that, hey, on this free body diagram, since AX equals 0, N is the only other horizontal force, so the normal force in this case also has to be equal 0. Next, let's do some of the forces in the y direction, right? If it points up, is positive, what do we have? Well, I got pointing up 366.6 newtons. I have pointing down minus 600 newtons. And the shear force is pointing down, right? So minus V. So here again, it's a little bit confusing because we drew here the shear force pointing down because that's the convention for the internal load for the shear force. Down is actually positive, but that doesn't mean that when I sum forces in the y, I just add V. No. V is pointing down and some forces, right? If something's pointing up, it's positive. This guy's pointing down, so it's negative. Anyway, so we would solve for V from this one. How would I do it? I would actually just move V to the other side, and I would have 366.6 minus 600, which gives me minus 233 newtons. That's for our shear load. And then finally, let's solve for the moment. So let some moments above point C. Remember, counterclockwise is always positive. So what do I have? I'm going to start at point C and sweep away. So I have my internal moment, which is the value I need to figure out. Remember, I drew it counterclockwise. That's the positive convention. That's what's going to make that beam smile if I need to kind of push it down like this to make it smile. So now that I look at the free body diagram, that's counterclockwise, so it's also positive. So that's why the M is positive right there. Okay, so next we have the 600 Newton force. The distance to the 600 Newton force is 0.5 meters. And if we're pinned here at C and we push down here on the left, it's going to make it spin counterclockwise. So that's also a positive moment. And then on the other end, we have the 366 force. So 366.6. It's a distance of 2 meters from A to C. And since we're pushing from the bottom and we're pin C, that's going to create a clockwise or a negative moment. And I believe that's it. We don't have anything else. So the sum of all of these must be equal to 0. When we solve for M on this case, right, I'm going to move all of this to the other side. So I'm going to have negative 600 times 0.5 plus, right, because I'm moving it to the other side, plus 366.6 times 2. And the number that I get is 433.2. What are the units? Well, we're working with forces in newtons and distances in meters. So there we go, 433.2 Newton meter. And we have the internal loads.